Good afternoon, everyone. I'm Yihan from Fudan University. I'm pleased to share our research vision identifying affected library versions for open source software vulnerabilities. This is a joint work with Kaifeng, Bihuan, and Xing. Open source software plays a crucial role in software development. According to Simpson's Supply Chain Security Report, open source software vulnerability has a substantial impact in supply chain security. Employing software composition analysis techniques is an effective way to mitigate such security risks. The common pipeline of SAA involves parsing and extracting dependent libraries from a target project. Then, it queries vulnerability databases to identify whether any vulnerabilities exist for these dependent libraries of a specific version. However, if the vulnerabilities affect library versions are inaccurate or incomplete, downstream tasks such as vulnerability propagation and exploitation may be impacted, causing false positives or false negatives. Essentially, the quality of the vulnerability database directly affects the effectiveness of SAA. Therefore, ensuring quality of vulnerability databases is of paramount importance. We first use one vulnerability to demonstrate the quality issue of current databases or approaches. There are 5 databases and 5 related approaches. However, there are only GitHub and GitLab adversaries that reported the true affected version. Other databases and approaches either record the wrong versions or not detected any vulnerable versions, raising the quality issues are prevalent. We use another CVE to demonstrate the quality issue. The vulnerability's root cause is when using the bcrypt class with the maximum work vector, which is 31. For log runs, the encoder does not perform any sort runs due to an integer overflow error which occurs in line 10 in the pre-patch methods. VSCZ is one of the SOTA approach to tracing the delete lines within patch to the inducing commit of the vulnerability. There are 2 main limitations of VSCZ. First, in this case, VSCZ regards each delete line as equal and wrongly tracing the line 22, 23, 28, and 29, which is vulnerability unrelated, caused 91 false positive versions in this case. Another limitation is that it cannot deal with the patch only with add lines because it depends on git blames to trace the delete lines and overlooks the fixed features, which can cause false negatives. Another approach is virjava, which also caused the false positives in this case. This is the function call of functions in the patch. It first checks the password in checkpw function, and during checking the password, the function invokes hashpw and crypt raw to perform the central password hashing step in the bcrypt class. Virjava not matched the vulnerable crypt raw in this version, which is appropriate because the fixed long runs is quite different from the int runs in the line 6. However, it is also reported by virjava as a vulnerable version because the uncritical checkpw function before change in this version is detected, which causes 84 false positive versions. There is another clone-based approach, MVP. It first slices the change statement to extract the vulnerability-related and fixed-related context. In this case, the line 22, 23, 28, and 29 is vulnerability unrelated statements, and the slicing further introducing more vulnerability unrelated lines of line 24, 30, 31, 32, and 33, which cause 136 unvulnerable versions matched as well. Body and Vision Finder is 2 clone-based approaches. They regard the function level match. In other words, they not consider the change statements but hashing the pre and post change methods to identify whether the version is vulnerable or not, which caused 136 vulnerable versions missed because of the cross signature. So, let's summarize the current patch-based and clone-based limitation. First, they consider all changed methods equally important. Besides, they either consider the changed statements equally or miss the importance of statements with function-level matching. This all caused false positives and false negatives. To distinguish the importance of vulnerable methods and patched statements, Vision performs critical method selection and critical statement selection to prioritize important changes and their context. Furthermore, the vulnerability signature is represented by weighted inter-procedure program dependency graphs that incorporate critical methods and statements. To distinguish the importance of vulnerable methods and patched statements, Vision performs critical method selection and critical statement selection to prioritize important changes and their context. Furthermore, the vulnerability signature is represented by weighted inter-procedure program dependency graphs that incorporate critical methods and statements. As for critical method selection, we use his algorithm, originally developed for rating web pages. In the context of vulnerabilities, authority methods are those that a satanizer would eventually reach, while hub methods are the triggers that are likely to be traversed. Additionally, intermediate methods lying between authority and hub methods are considered during the scoring iterations. Take the same CVE as an example. There are a quatrain of HPW to crypto. We first construct the core graph, then add the additional knowledge about the method and class of the vulnerability from GitHub. If any class or method is mentioned, like crypto in this case, Vision phantom method caller for it. Eventually, the method relation graph is constructed and the critical method is determined by hits. Next, Vision identifies the critical statements. Taking the same CVE as an example, it first slices the change statements to extract the vulnerability-related and fix-related context. Then, the Vision identifies the critical variable, which is full check, introduced in line 1 using HuntDiff, while other variables are uncritical. After that, Vision uses taint analysis backward and forward to trace the taint path of full check to get the critical statements. To evaluate Vision, we construct a large scale of databases with a high coverage and accuracy. It contains 12,073 library versions corresponding to 102 CVEs across 36 distinct CWE types within 79 libraries. Next, Vision constructs the IPDG. First, it leverages Unix coder to vectorize the node and edge in the IPDG and weighted the critical statements identified before as WS, while the edge's weight is the average of its source and the destination. After that, the vulnerability signature IPDG pre and the patch signature IPDG post is constructed. Then, Vision maps the critical functions and the critical statements to the target repositories, and then runs the same pipeline mentioned before to construct the potential vulnerability signature and the potential patch signature. Finally, it uses graph added distance to calculate the similarity of IPDG. If the vulnerability similarity is greater than the patch similarity of signature, while the similarity of vulnerability signature is greater than 0.6, the target repository version is vulnerable. Otherwise, it is the safe version. Then, we do an ablation evaluation. It shows that removing any component of vision results in a noticeable drops in precision and recall. Critical statements have the highest contribution on recall, underscoring its importance, while correlations have the highest contribution to precision, highlighting its importance. Besides, Vision have reported a lot of incorrectly labeled vulnerabilities to the 5 vulnerability databases and received many thanks letters from GitHub, GitLab, and NVIDIA. Others are in progress, which shows the usefulness of Vision. Last but not least, don't be hesitant to contact us if you are interested in our work. That's all. Thank you for your listening.